All right, so part 3, we're going to get into trigonometric ratios of any angle. So we're going to talk about both the unit circle and reference triangles, review a little bit of special right triangles, a little bit of everything just to close this all up. So first thing, reference triangles. I mentioned this briefly in one of the previous videos, but a reference triangle is using a reference angle and then dropping an altitude to create a full triangle. So you can use your reference triangle to find trigonometric ratios by using something like SOHCAHTOA or some other tricks. Just keep in mind what the signs should be, and for that we're going to remember that all students take calculus to give us the positive trig ratios in each quadrant. So something that you might start picking up on from doing trig ratios in any quadrant is if we have a triangle or a point drawn in, the hypotenuse we're going to refer to as r because it kind of acts like a radius. The length of r is equal to x squared plus y squared, Pythagorean theorem, r squared equals x squared. And then the trig values, to get sine, it's y over r, cosine x over r, tangent y over x, and then don't forget your reciprocals would be flipped versions of all three of those. So as we start applying this to the unit circle, they become a little bit more useful because we keep the r value, or the hypotenuse, equal to 1. And literally in the unit circle, the radius is 1. And for the most part in the unit circle, we use all the angles from special right triangles. If you need to review this, I'm going to put a star next to it. You need to let me know if this little memory jog isn't enough. If you need this in a more in-depth review, please let me know. So on the unit circle, since r equals 1, if we do y over r, that reduces to just y. Same thing with cosine, x over r becomes x, and then tangent, oops, sorry, I didn't finish writing that out. Tangent is just y over x, that one didn't change. Here's a fuzzy version of the unit circle. So a complete unit circle has angles in radians and degrees, and it has the coordinates where those angles intersect the unit circle itself. So if we're using the special right triangles on the unit circle, and I just noticed these are a little misleading down here. Because they're not drawn to scale enough. On the unit circle, all of these values are going to be 1, so the other side's just. So basically, to make this equal to 1, I'm going to divide each side by root 2. And then I'm going to have to rationalize this. So the two legs become root 2 over 2. Whereas the hypotenuse becomes 1. Divide all of those by 2. We're going to get 1/2 on the short side, root 3 over 2 on the long side, and then 60 degrees is reverse, root 3 over 2 on the long side, 1/2 on the short side. Sorry if I went too fast. You might need to rewind and pause. So those coordinates appear on the unit circle itself. So here, 30 degrees, the long side is along the x-axis, so we get an x-coordinate of root 3 over 2. It's hard to read, that's what that is. So the x value is the long value, root 3 over 2, and the y value is the short one, 1/2. At 45 degrees, we have root 2 over 2, and at 60 degrees, we have the flip version of 30 degrees, we have 1/2 over root 3 over 2. So if we want to find the 6 trigonometric functions of 120 degrees, I'm going to sketch that real quick. That's less than 180 but more than 90, so that's going to be somewhere in here. I'm going to determine that the reference triangle has, let's see, if my reference angle is 60 degrees, I'm going to put 60 degrees here. Let's use the unit circle, so let's make r equal to 1, which means we're going to be using this version of the triangle, where we had 1 here, root 3 over 2, and 1/2, but everything gets flipped around. Y is still positive, but now we're going in the negative direction for x. So the 6 trigonometric functions of 120 degrees use these 3 values here. I'm going to jot them down, I'm going to pause, jot them down, and then you can take a look at them. Okay, so there's sine, cosine, and tangent. The only hard one is tangent because we have to take the y value divided by the x value. I forgot my negative signs. Here we go. So when I take root 3 over 2 divided by negative 1/2, remember to flip the second fraction and then multiply straight across, so the 2's end up canceling. All right, I'm going to pause and write the other 3. So here's what they look like when I just flip them to find the reciprocals, but I need to rationalize the denominators. So I would need to multiply this by root 3 over root 3, which simplifies to 2 root 3 over 3. This just simplifies to negative 2, and this would simplify to 1 over root 3, negative 1 over root 3, and when I rationalize that, I get negative root 3 over 3. So lots of dividing and multiplying by fractions and rationalizing denominators. Please let me know if you need me to review either one of those with you. So finding the 6 trigonometric value functions at 315, I'm going to draw a quick sketch, get my reference triangle. 315 is down here. So that makes my reference triangle 45, 45, 90. My hypotenuse will use 1, we'll use the unit circle, which makes my other 2 sides some version of root 2 over 2. Keeping the y negative because I'm in the 4th quadrant. So from here, I get sine and cosine from y and x. Tangent is y divided by x. So that's a negative root 2 over 2 divided by positive root 2 over 2. So that's like taking a number and dividing it by itself, only with one other sign in there. So actually tangent is going to be negative 1. And then the reciprocals, if I flip root 2 over 2, I'm going to have to rationalize that. So I'm going to end up with just root 2. Because I'll get 2 in the denominator, 2 root 2 in the numerator, and those 2 cancel out. So try this. Try find the cosine of 210. If possible, or if necessary, use radicals for that. The quadrantal angles are the angles that are on the x and y axis, so 90, 180, 270, 0, 360, and all of the multiples. We just extend the pattern to those. We use the coordinates here. So if I were going to write down the 6 trig values of pi over 2, sine, and I'm being lazy and just writing sine and not writing the angle. Sine is 1, cosine is 0, tangent should be 1 over 0, but that's undefined. I can't divide by 0. Cosecant is also 1 over 1. Secant would be 1 over 0. That's undefined. And cotangent would be the reciprocal of undefined, which, just like you saw in cosine and secant, is 0. So I want you to try this one on your own as well. Find the tangent of 3 pi. If it's not a quadrantal or special angle, you would just use your calculator without, and you would get decimal answers. You wouldn't be able to get exact answers. Let the hypotenuse equal 1, but you would need at least one other side, or you would need to know the angle. Make sure you sketch the angle first so you can get your reference triangle. Like, so for example, the cosine of 130, that's somewhere in this quadrant here, where my reference angle is 50 degrees. So if I call the hypotenuse 1, I would say I have the cosine of 50 degrees is equal to x over 1. Solve for that in my calculator, and then change my answer ultimately to a negative. So that answer here, if we take the cosine of 50, we get 0.6428. And we would just need to know that the cosine should really be negative here. So it should be negative 0.6428. You could also plug into your calculator cosine 130, and it will go ahead and change the sign for you. It'll tell you it's negative. Okay, that's it. It was a really long one. Sorry if that was too much review for you, or sorry if it was not enough.